Good, welcome to today's class. So last time we introduced Pascal's triangle. We tried to have some table of expansion in few binomials. So where these are just integers. This was just 1 because any number, any real number to the power of 0 is 1. And then if you raise any number 1, you get the number itself plus b. And then here we get a squared plus 2ab plus b squared. We went up to 3. So this is a cubed plus 3a squared b plus 3ab squared. Maybe let me make it 4. So let's make the 4 plus 4, the 3b plus 6, a squared b squared plus 4, ab cubed plus b to the 4. And there are some few observations I made. So number 1, you observe that in each and every term, if you add the powers, you get the value of the integer to which the power is being raised. For example, in this case, the term is just one term, but here is a power 0 and b power 0 and a power 1. So 1 plus 0 is 1. And here you have each and every term. For example, a squared, there's a b power 0. So 0 plus 2 gives you a power 1, b power 1. 1 plus 1 gives you 2. Same as when you go to 4. A power 4, there's a b power 0, and a power 3 plus b power 1 plus 3 gives you 4. 2 plus 2 gives you 4. The other observation we made is that in each and every expansion, there are n plus 1 terms. So when you're raising to 0, you get 2 plus 1 terms. That means you get 1 term. When you're raising to 1, you get 1 plus 1 terms. That means you get 2. When you're raising to 2, you get 2 plus 1. That means you get 3. 1, 2, 3. And this process continues for all positive integer values. The same for example, 4 you are seeing we have. And now from this, we extracted the coefficients that gave us the Pascal's triangle. So in the first expansion, you have a 1. In the second expansion, you have just 2 coefficients, 1 and 1. In the third expansion, there's the coefficient of a squared, there's the coefficient of ab, and the coefficient of b. In the fourth expansion, there is 1, there's a squared b, there's a coefficient of ab squared, and a coefficient of b cubed. And then lastly, in 4, there is a coefficient of a cubed b, then coefficient of a squared b squared, then coefficient of ab cubed, and last coefficient of b cubed. This is the famous Pascal's triangle. Now, once we understand this Pascal's triangle, we'll be able to come up with binomial coefficients for any positive n that you're interested in. So one observation you can make from this, actually this is an example of a sequence. You observe that in the first row there's a 1, the second row there's 1 and 1. Now for you to get this second row from the first row, you start with 1. There will always be 1s at the ends, but for you to get these 2, it's 1 plus 1. Moving to the third row, so there's a 1, and then for you to get this 3, add 1 plus 1. For you to get this 3, you add 2 plus 1. For you to get this 4, it's 1 plus 3. For you to get this 6, it is 3 plus 3. For you to get this 4, it's 3 plus 1. So if I was to get 5, let us see. What will be my next coefficient here? I'm going to 5. What will be my next coefficients for 5?
5.
5.
10.
And then after 5?
9.
How did you get 9?
10.
10.
Add
10,
3.
10, 10,
10. So 4 plus 6 is 10. And then after 10?
10.
Again 10. And after that?
5.
5. And lastly, it's a 1 at the end. Good. So let us first of all see how we can use this Pascal's triangle to do some few binomial expansions before we generalize to binomial theorem. I will show you why this is not a very efficient method for generating binomial coefficients. So these terms here are called binomial coefficients. These terms that you see in this Pascal's triangle, they are called binomial coefficients. So suppose we want to expand a plus b raised to 3. I know you've seen it, but how can we expand a plus b raised to 3 using the Pascal's triangle? So in the Pascal's triangle, the first row is use it when you're raising terms to power 0. The second row when you're raising terms to the power 1. The third row when you're raising terms to the power 2. The fourth row when you're raising terms to the power 3. The fifth row when you're raising terms to the power 4. And the sixth row when you're raising terms to the power of 5. It goes on and on forever. So now I have a plus b cubed. I need to use the terms in the fourth row. So my coefficients will be 1, 3, 3, and 1. So the first thing you do is to obtain the binomial coefficients. I'm doing a plus b cubed, so I go to the row for 3, and I have my binomial coefficients 1, 3, 3, and 1. Once I have the binomial coefficients, then the observations we made about the trends. So first thing is that the powers of the first term will be decreasing by 1 from the first term to the last term. So we start with the powers of the first term. We give it the highest power 3. In the second term, we replace this by 1. So we give it a to the 3 minus 1, which is 2. Next, we less this by 1. So instead of a squared, we have a power 1. And then lastly, 1 minus 1, we have a to the 0. That is for the first term. Start with the highest power and keep lessing by 1 as you go. Then you come to the second term. In this case is b. Start with the lowest power. The lowest power in this case is b. So in the first term, we have b raised to the 0. In the second term, we'll increase the power of b. So we now have b raised to 0 plus 1, which is 1. So it's b power 1. In the next term, we increase the power of this b. So b power 1. So here we have b power 1 plus 1, which is b power 2. Plus, lastly, we increase the power of b here from 2 to 3. So we have b cubed. Notice that in each and every term, so this is what I'm calling, so this is these are the terms that I'm referring. In each and every term, if you add the exponents, you always get the exponent, you always get n in this case. In this case, you're getting 3. So in the first term, 3 plus 3 is 3, 2 plus 1 is 3, 1 plus 2 is 3, and
Sure.
2 plus 3 is also 3. Yes. Go ahead.
Isn't the 3 a power? Why are you writing it as a number?
It's a power.
Yeah, but where is the 3a squared b1 coming from?
Oh, you missed something. So let's go over it again. You want to expand a plus b to the cubed. The first thing you need are the binomial coefficients. And you obtain the binomial coefficients Pascal's triangle. So in this Pascal's triangle, I will need the binomial coefficients for the row, the fourth row, when I'm raising to the power 3. And the binomial coefficients in this case are 1, 3, 3, and 1. So first thing, I start by writing down the binomial coefficients. 1, 3, 3, and lastly 1. That is your first step. Now, second step, we now want to make the use of the observations we made last time, the last class. So take the first term and then start it off with the highest power and keep decreasing the powers up to 0. First term in this case is a. So in the first coefficient, I start A off with the power of 3. In the second coefficient, I have A with the power of 2. So to get 2, I've subtracted 1 from 3. In the third coefficient, I have A to the power of 1. So I have subtracted 2 from 1. I've subtracted 1 from 2 to get 1. In the last term, I have A power 0, where 0 is 1 minus 1. So you notice that I've started with the highest power, then I've less them until the last term. Then now the second term, which in this case is B, started off with the lowest power, which is 0. Then in the second term, increase this 0 by 1. So we have B raised to 1. Keep again increasing this, so from 1 to 2. And then lastly, from 2 to 3. So this will be your expansion. So A plus B cubed is simply A cubed. So here, remember B to the 0 is 1. So I have 1 times A cubed times 1, simply A cubed, plus 3 A squared B, because B power 1 is just B, plus 3 AB squared, because A power 1 is just 1. The last plus B cubed. Two things to keep in mind. Number one, first step is to obtain the binomial coefficients. Then number two, start off with the highest power for the first term and keep reducing the power by 1 up to 0. And then start with the second term at the lowest power and keep increasing up to 3. Any question? Any question?
Yes, sir. Yes.
Yes.
Could you go over the problem, please?
Okay. We want to expand A plus B. 3. We want to expand A plus B cubed. So the first step is obtain binomial coefficients. Obtain binomial coefficients from Pascal's triangle. Have Pascal's triangle. So the one that corresponds to 3 in this case is this row that contains 1, 3, 3, and 1. So my binomial coefficients here are 1, 3, 3, and 1. That's what I start with. Then next, the second step, I take the first term. In this case, the first term is A. And I started off with the highest power at the first coefficient. And then subsequently, I decrease the power by 1 until when the power is 0. So that means I start here with A power 3. The second term, I have A power 2, where 2 is just 3 minus 1. In the second term, I have A power 1, where 1 is 2 minus 1. Then lastly, I have A power 0, where 0 is 1 minus 1. So I stop at 0. Move to the second term, in this case, B. Start B with the highest, with the lowest term, which is 0. And then keep increasing the powers of B until you get to 3. Well, another way to do that is we observe that the sum of the exponents must always be 3. So what you can do, this is A to the 3, and you need a B, but you want the sum of these exponents to be 3. The only way that can happen is when I have here B power 0, so that 0 plus 3 is 3. Then I move to the second term. I have an A squared, but I want that the sum of the exponents must be 3. So what do I need to add to 2 to make it 3? It's 1. So I have B raised to 1. In the next term, I have an A power 1. I want terms so that the sum of the exponents would be 3. What do I need to add to 1 to make it 3? It's 2. So I have here B power 2. Lastly, I have a power 0. What do I add to 0 to make it 3? It's 3. So I have here b cubed. So that at the end of the day, you have a cubed plus 3 a squared b plus 3 ab squared, put a plus here, plus 2 plus b cubed. I could also do the same thing in the reverse order. This process is symmetric. I could start with the first term and decrease the powers, then increase the powers of the first term. I will still get the same answer. So let me show you what I mean. So I start with the coefficients are 1, 3, 3, and 1. The second term is b. So start with b cubed plus a to the 0, followed by b squared, a to the 1, followed by b, a to the 2, then followed by b to the 0, a to the 3. So when I simplify this, this is simply b cubed plus 3 ab squared plus 3 a squared b plus a cubed. You all know that multiplication and addition of real numbers is commutative. So it doesn't matter whether you start with from the left or the right. So these are actually the same numbers. These are the same numbers. Both are identical. They are expansions of a plus b cubed. Question? Any question? Any question? Okay. One more example before we. Let me give you one more example. This time around, we want to expand 2x minus y raised to the power of 5. 2x minus y raised to 5. Well, you could write this as 2x plus negative y raised to the power of 5. So that I have a binomial and my first term is 2x. My second term is minus y. So this is the binomial I want to expand. So in the previous one, we're dealing with a plus b. This 2x is now playing the role of a, and minus y is playing the role of b. Sorry? Hello?
Yes, we can hear you. Oh,
What's the problem? Hey, what's the problem? So in this case, we have the coefficients 1, 5, 10, 10, 5, and 1. So we have 1, 5, 10, 10, 5, and 1. Those are the coefficients which you have obtained from the Pascal strap. Now we start off with the first term. In this case, the first term is 2x. So we'll have 2x raised to the power 5. And then we have 2x raised to the power 4. And then we have 2x raised to the power 3. This thing is not looking nice. Let me write it again. So 1, 5, 10, 10, 5, 1. I'm starting with 2x for 5. Then I have 2x 4. Then I have 2x cubed 2x squared. I have 2x power 1, and I have 2x power 0. So I'm done with the first term. I'm starting with 5, I've decreased the powers up to 0. Now I move to the second term, which is minus y. And you have to be very careful with this symbol, with this negative sign. So minus y raised to 0, then minus y raised to 1, and then minus y squared. Notice that I'm ensuring that the sum of these exponents is always 5. 0 plus 5, 4 plus 1, 3 plus 2. Now 2 plus 3. And now 1 plus 4. And lastly, 0 plus 5. Okay. So first term, minus y to the 0. What's that? What's negative y raised to 0?
1.
1. So we have here 2 to the 5, which is 32, x to the 5. Plus, the first term will simplify as 32x power 5. 32 is 2 power 5. Now next we have a 5, then we have a 2x power 4 and a minus y. So the overall sign here will be minus y, minus 1 because of this minus. And then, of course, you will have x to the 4 and y. Now I need what to write here. This is going to be 5 times 2 to the 4. So 16 times 5, that's 80. Plus, in the next term, we have the negative sign has been squared. So it's a negative y squared. So we'll have plus as the overall sign. Then, of course, we expect x cubed and y squared. And now we have 2 cubed, well, that's 8. So times 10, that is 80. Plus, next, we will have the negative. We have a minus y cubed. So this will be minus x squared y cubed. And then the term that will come here is going to be 2 squared times 10. So that's 4 times 10, which is just 40. And then plus, because minus 1 to the 4 is 1. Negative number raised to an even number is positive 1. So, and then now we have x and y to the 4. 2 times 5, that is just 10. And then lastly, 2x power 0 is going to be 1. Minus 1 to the 5 is minus 1. So there's this minus 1. Then y to the 5. So this is the expansion, 2x minus y to the 5. Any question on this? Any question on this? So simple, good. Now, it's not, using Pascal's triangle is not one of the nicest things you want to do as a mathematician, because this is, you're building up a recursive sequence. Recursive sequence, we said these are sequences for which the subsequent terms depend on the previous terms. So for me to have generated these terms for 5, I need to know what are the terms, what are the coefficients for 1, what are the coefficients for 2, 3, and 4. Because for me to obtain this, I need to know coefficients 4. For me to know at 4, I need to know the ones at 3, all the way. So suppose someone asked you to, let's say, have x plus y raised to the power 1000. This means you will have to build up 999 rows before you get to this 1000th row. And mark you, the 999 rows are useless. You're not interested in them. I'm not interested in the coefficients for 5, 10, 6, but I'll have to put them if I were to use Pascal's triangle. So this is very inefficient. It's laborious, and we have to find an alternative way of getting around binomial expansion. Okay, so that I will only get the specific coefficients that I'm interested in. I don't need to know, if I want to do an expansion to the power of 5, I don't need to know coefficients for 4, 3, 2, 1, and 0. Now to do this, I will introduce the binomial theorem. But before the binomial theorem, there are some few definitions I would like to make. The first definition is the factorial notation. Now in this class, I will only define factorial for positive real numbers, positive integers, or natural numbers. Remember, those of you who have done or will do gamma functions, factorial notation is there for fractions and even negative numbers. But for this class, we will deal with positive integers. Let n be a positive integer. Let n be a positive integer. Then n factorial written as n and then this exclamation mark. So this is read as n factorial. And it means you're taking n, you multiply by n minus 1, multiply by n minus 2, you keep on doing this until you get to 3, 2, 1. Or another way of doing it, because we know multiplication is associative and commutative, I could start from 1. So 1 times 2 times 3, all the way to n minus 3, n minus 2, n minus 1, then n. Let me give you some few examples. For example, 4 factorial is simply 4 times 3 times 2 times 1. And this should give you 24. 3 factorial is simply 3 times 2 times 1, which will give you 6. Lastly, 5 factorial is 5 times 4 factorial, which should give you 120. So in other words, if you have a positive integer, to obtain the factorial of that integer, take all the positive integers that come before that integer from 1, and then multiply, get that product. So to get for 4, I need all the terms that are below 4, which are 3, 2, and 1, and then I find this product. To get for 5, I need all the terms that are less than 5, and then I multiply to get this product. Any question about this factorial? Perhaps you're wondering, why do we need this factorial? What's the motivation? What's the motivation for this? Suppose you have 3 letters, A, B, and C. Or let me write this as a set. You have the set A.
No aliweke
Nani joana kuikara au sometimes you going to go jari more than a.
So suppose you have this set of the elements 1, 2, 3. Then you asked, in how many unique ways can you arrange the numbers? So I could write firstly as 1, 2, 3. Or I could fix 1 and switch 2 and 3 and have 1, 3, 2. I could change the position of 2 and 1 and have 2, 1, 3. Then I could fix 2 and switch 1 and 3 so that I have 2, 3, 1. Well, I can also reverse this and start with 3 followed by 2 and then 1. Then here I can fix 3 and switch 2 and 1 so that I have 3, 1, and 2. Is there another way of arranging these numbers, these 3 numbers? Can you think of another way of arranging these 3 numbers that is different from the ones I've written here? Anyone want to try? Maybe 3 is too big. Huh? Maybe 3 is too big. Let me give you 2. It should be simpler. Suppose you have a set which contains the elements on 5. In how many different ways can you arrange these numbers? In how many ways can you arrange these numbers? You could write them as 4, 5, or you could write them as 5, 4. Is there any other way of arranging them?
No.
No. Good. So what's the connection between this factorial? What we have done here is called permutation, finding a unique way of arranging a given number of elements. Notice that, so this is 1, 2. There are 2 ways of arranging this. So there are 2 ways. This number 2 is simply the cardinality of the set. So the set has how many elements? 1 and 2. 2 factorial. What is 2 factorial? By definition, 2 factorial should be 2 times 1, which is just 2. Same for the set A. Cardinality of A is 3. So the distinct number of ways for arranging the elements in a set of cardinality 3 should be 3 factorial, where 3 is the cardinality of the set, the number of elements. 3 factorial we have just seen should be 3 times 2 times 1, and that gives you 6. And it is true, we have 6 different ways of doing that. It turns out that this same procedure can be applied to binomial expansion. Now let me introduce combination. So definition. We define N combination R for R and N both greater or equal to 0. They're positive integers. R and N are positive integers. As the number, we write this as N combination R, NCR. Some books will write this as NCR, N as a superscript before C and then R as a subscript. And this mathematically is written as N, we read this as N combination R. So it's just a matrix with 2 rows in 1 column. And the definition of this is N factorial divided by R factorial times N minus R factorial. And because our definition of factorial, we are only dealing with positive integers, we don't want this quantity to be a negative number. So N must always be greater than R, greater or equal to. N must be greater or equal to R. Otherwise, you need a more advanced sum to deal with situations when R is greater than N, but you don't do N combination R. Well, this simply means different ways of choosing a certain number of items from a set. Let me give an example. Let me give an example before we look at that definition. Suppose you have just the set that we have 1, 2, 3. Then you're asked, in how many different ways? No? Now the question is, in how many different ways can you choose no item? So I want you guys to answer this question. Number 1, no item. Number 2, 1 item. Number 3, 2 items. Number 4, 3 items. Maybe let me be ridiculous and ask you 4 items. So we have a set 1, 2, 3. Let me change things a bit to avoid confusion. Always work. Let me have A, B, and C instead as the elements of the set. So the first question, in how many ways, different ways, distinct ways, will you be able to choose no item from this set? The set has A, B, and C. How many different ways will you be able to choose no item from this set? Hello? The question seems so hard. Hello, anyone wants to try? Hello? Is it too abstract?
Yeah, I've tried, but at the bottom I found 0, so it's not defined. I don't know.
Bottom 0? Yeah, of course, you cannot choose 4 items from a set containing 3. So that's perfectly okay. You cannot choose 4 items from a set with 3 elements. So the bottom one we have 0. How about any of this? You can try for any of this that we have. You see, it's not about getting the right answer. I just want to see how you guys are thinking.
The fourth one is 6.
The first one is 6.
The fourth one.
The fourth one.
The one for 3 items.
The one for 3 items. You're saying it is 6. But there are only 3 items. How many elements do you have in your set? Let me try to make it practical. Are you able to see what I'm carrying in my hand? Hello?
Yes.
So
Yes.
this is the set so they're talking about. It has 3 elements. There's a blue pen, a black pen, and this duster. So what I'm asking you, in how many different ways can you choose 3 items from this set? The order does not matter. I could arrange them like this, I could put them like that, but they still remain 3 items. First of all, the case of 4 we have ruled out. The case of 4 has been ruled out. You cannot choose 4 items from here because I only have 3 items. So this is not possible. In fact, it's not even 0. It's not possible. There's nothing like that. Here I should write undefined.
1.
Yeah, there's only one way because you only have 3 items. So the first, this is the fourth one. So here we have 1. Now I will make a connection with this combination. How about now 2 items? In how many different ways can you choose 2 items from this set?
2. You can only choose
Are you sure? Okay, let's do this. So this is the first way. Choose the pens. The second way, I can take a pen and this one. The other way, I can take this pen and this one. Any other way?
And
sorry? I'm only choosing 2 items.
Yeah, but 3 ways.
Let's do it again. First way, you take the pens. Second, you take 1 pen and the duster. Third one, you take the other pen and then the duster.
So 3.
There
are only 3 ways. 3. Good.
Oh, okay.
How about 1 item? How many different ways can you choose 1 item from this set?
1, 3.
3.
3.
Yeah.
Can someone explain why you're choosing 3? Why you're saying 3?
Because you can only pick one item once.
You can only pick 1 item once. You can choose this pen or choose this guy, or this other pen. So it's 3. How about no item? I give you a set with 3 items. In how many different ways will you decide not to choose anything from my set? Say, I don't like what you're giving me. I'm not taking it. I'm not taking anything. How many different ways?
0.
Are you sure it is 0?
1.
No
It's
item.
only 1 way of rejecting, so it's going to be 1. Can someone make a connection with the Pascal's triangle? Are you seeing something related to the Pascal's triangle? The value of our set is 3. Math is always connected. One way we're choosing items from a set, the same concept, we want to apply it in doing binomial expansion. And for those of you who will go, maybe you have seen this before, this problem is also in the probability theory. You will deal with these commutations and combinations. So there's always a connection between these concepts. If you remember so well the table we had, these are the binomial coefficients when you have 3, because you're seeing 1, 3, 3, and 1. It's simply the different ways, the possibilities of choosing items without any order. You're only considering the number of items being chosen. Remember, for the first item, I could choose A, or I choose B, or I choose C. Only 3 ways. For the second one, I could choose A and B. Well, whether I choose A and B or I choose B and A, this is only 1 because there are only 2. Or I could choose A and C. Whether I choose A and C or C and A, it's the same. Still the same elements. Or I could choose, what's the other one? A, B, A, C, B, C. B, C. Whether you choose B, C, or C, it's the same. So there are only 3 ways, 1, 2, 3, of choosing 2 items from this set. Okay? And then 3 items, you can only choose everything in the set. And that's only once. So let's make a meaning of this expression. Remember the question I asked you, for 1, you could just compute 3 combination 0. I've given you a set of 3 items. You have decided not to choose anything. And 3 combination, 0 by definition. So remember, n combination r has been defined as n factorial divided by r factorial times n minus r factorial. So this, in this case, my n is 3. So n is 3. And my r is 1. I just use this formula the way it is. N is 3, so I have here 3 factorial. Divide by r is 0, so I have 0 factorial. And then 3 minus 0 factorial. We'll see what that, you work out that and give me.
You just wrote r is 1, then you said r is 0.
Sorry, r is 0. because we're choosing no item 0.
Okay.
Yes. The second one should be 3 combination 1, which is going to be 3 factorial divided by 1 factorial times 3 minus 1 factorial. Work out that. The next one should be 3 combination 2, which is 3 factorial divided by 2 factorial times 3 minus 2 factorial. Lastly, we'll have 3 combination 3, which is 3 factorial divided by 3 factorial times 3 minus 3 factorial. So what are you getting? For the first one, what do you get? What is 0 factorial?
1.
I expect someone to ask that. So 0 factorial is 1, and it's very easy to prove that 0 factorial is 1. So 0 factorial, take it as a definition. 0 factorial is 1. It's very easy to prove, but one of the ways to explain that is given a finite number of sets, the only way you can reject everything is 1, choosing 0 items. So that's why 0 factorial is 1. But there is a rigorous mathematical way of proving that 0 factorial is actually 1. So what do we have here? What do we have here?
6 over 6.
Which is 1.
1, yeah.
Good. The same one that we had before. How about this guy?
Six over 2, which is 3.
Plus 3. Make sure you understand this, because this is all you need to understand for you to do binomial expansion. Make sure you understand how to compute the factorials. What does it mean for n combination R? How about this third guy?
Three.
3. And then lastly, what do you have?
1.
1.
1. And you notice that they are identical to the responses that we have. Different number of ways of choosing some finite number of items from this finite set. So this is the connection between cardinality of a set, choosing a given combination of items from the set, and arrangement, permutation, and combination. Now we are going to use this to do binomial expansion. Notice that in this case, we can do something cubed without having to draw Pascal's triangle. I don't need to know what are the coefficients for n is 2. What are the coefficients for n is 1. I can straight away compute coefficients of 3. Is there any question? Any question? Good. Now let us state the binomial theorem. We'll state the binomial theorem. Should be using binomial expansion. The binomial theorem. Binomial theorem. This is the last theorem we're learning this class. Let A and B be real numbers. Well, they could also be complex numbers. The theorem will still work. And N a positive integer. Actually, N and R. N and R positive integers. Then A plus B raised to the power n. Well, this is the same as n combination 0 times a power n plus n combination 1 times a power n minus 1b plus all the way to n combination n. Then a raised to 0, b raised to n, which we can write using the sigma notation as summation from k is 0 to n. We're doing this over the index k, so n combination k, and then a raised to n minus k, b raised to k. This is the famous binomial theorem. Given any binomial, which is just 2 terms, raised to n combination 0 is the first coefficient, n combination 1 is the second coefficient, n combination 2, we go all the way up to n combination n, which will be the n plus 1, the n plus 1 coefficient. And in sigma notation, you can write this as summation over k. K here is simply a dummy variable. I could use anything. I could have used j, I could use k, I could use y, I could use anything. You're summing from k is 0 to n. So this means at k is 0, I substitute k is 0 here. So n combination 0, and then a raised to n minus 0. So that's a raised to n, b raised to 0. I get this first guy. Then I add, at k is 1, I have n combination 1, which is this guy. And then a power n minus 1. So k is 1, so n minus 1. And then b power 1, which is this guy. Go all the way up to n. This is the binomial theorem. Any question on the theorem before I show you how to apply it? Any question on the theorem? Let's do an example. Example. Evaluate for x minus 7y or 3, even power 2. Let's take power 2. 4x minus 7y squared. So remember, this is the same as 4x plus negative 7y squared. So I have 2 terms. First term is 4x. Second term is a minus 7y. I want to use the binomial theorem. So what I will do, where there is n in the theorem, I replace with 2. So that means I will have a plus b squared, and then this n becomes 2. This guy becomes 2. This guy becomes 2. 2 minus 1 becomes 1. I don't need all this. I don't need a third term. Plus 2 combination 2 of a raised to 0, b raised to 2. So now for this guy, a is playing the role of 4x, b is playing the role of minus 7y. Okay. So what you will have is that 4x minus 7y squared, this should be 2 combination 0 multiplied by 4x squared, and then minus 7y raised to 0 plus 2 combination 1 multiplied by 4x power 1, then minus 7y power 1 plus 2 combination 2. So we stop at 2 combination 2. And then 4x power 0 minus 7y power 2. So let's see. What's 2 combination 0? You must remember this n combination r is n factorial divided by r factorial times n minus r factorial. So when you had 2 combination 0, 2 combination 0, same definition, 2 factorial divided by 0 factorial times 2 minus 0 factorial. Well, this is just 2 factorial divided by 0 factorial is 1, 2 minus 0 is 2, divided by 2 factorial, give you 1. So this guy is 1. Good. 4x squared. What's 4x squared? Hello? What's 4x squared? We've dealt with such polynomials before. 4 squared is 16, so this should be 16x squared. This guy power 0 is 1. First time we have 16x squared. 2 combination 1. What's 2 combination 1? Someone compute that. We'll also need 2 combination 2. Just apply the definition.
Combination 2, 1 into bracket 2 minus 1.
Factorial, then 1 factorial, 2 minus 1 factorial, which should be? What's the final answer at the end of the day? Because up here you have 2 factorial, which is 2. And then down 1 times 1, which is 1, so that's 2. So here we have 2. I have a 4x and a minus 7y. So this sign automatically will change to minus 4 times 7 is 28. 28 times 2 is 56 xy plus, lastly, 2 combination 2. Of course, that's going to be 1. Because you'll have 2 factorial divided by 0 factorial times 2 factorial. And then 4x to the 0 is 0. Minus 7y squared should be 49y squared. This is the expansion of 4x minus 7y squared. Just to say. Binomial theorem. And because 2 is a small number, we can expand this and check if it is really this. Let me expand. So 4x minus 7y times 4x minus 7y. That is what it means for something squared. So then take all the terms in the first bracket, use them to multiply all the terms in the second bracket. So we have 4x multiplied by 4x minus 7y. So this minus 7y multiplied by 4x minus 7y. 4x times 4x, that is going to be 16x squared minus 4x times 7y is 28xy minus 7y times 4x is minus 28xy. Minus times minus is plus, so 7 times 7 is 49. So this is plus 49 y squared, and you end up with 16x squared. Put these guys together, 6xy plus 49 y squared. And this is the exact same thing you have this side. Now that you know the binomial theorem, I can ask you to expand something to the power of 2000 or 5 million. It will be simpler because you won't have to find all the preceding binomial coefficients. Any question? Any question on binomial theorem? Any question on binomial theorem? The last thing I want to show you today is finding a specific term in an expansion. So finding or obtaining a specific term. So generally, in the expansion of A plus B by N, to obtain the term that contains A to the R, we compute N combination N minus R, A to the R, B to the N minus R. So if you are asked to obtain a term that contains A to the R, you only need to compute N combination N minus R times A raised to R, B raised to N minus R. Let me give you a very simple example on this. So suppose I ask you, obtain the term that contains x cubed y squared. The expansion x plus 2y raised to 5. Obtain a term that contains x cubed y squared. The expansion of x plus 2y to the 5. So of course, straight away, this the rule tells you that you need to compute. So I'm looking for x cubed. I can choose x cubed as my A to the R. So I need to compute 5 combination 5 minus 3, where my N is 5, because it's raised from 5. My A to the R is x squared cubed, because I'm looking for a term that contains x cubed. Automatically y squared will come, but I could also use y squared. I've decided to choose x cubed. And then here, I should have x, the first term, cubed, and then 2y raised to 5 minus 3. So what does this give? 5 combination 2, then it's an x cubed, 2y, so 5 minus 3 is 2, 2y squared is just 4y squared. What's 5 combination 2? 5 combination 2? Five combination 2 should be 10. There are 10 different ways of choosing items, choosing 2 items from a set of 5. So you just need to compute 5 factorial divided by 2 factorial times 3 factorial. Well, so this is going to be 5 times 4 times 3 factorial divided by 2 factorial times 3 factorial. 3 factorial, and then 2 divides 4, so you have 10. So I've taken 10 times 4 to get 40, then I have x cubed and y squared. So in this expansion, this theorem or lemma tells us that the term that contains x cubed y squared will be 40 x cubed y squared. We can do this expansion to verify if this is true. Let's do the expansion and verify if this is true. Hello? Yes. You have a question?
Could you just give me some more time? Let me write this quick. I'll just snap it for you, Rich.
This one.
Yeah, let me just snap it.
I want to erase this part because I want to use it. I want to give this part because I want to check.
Yeah.
How much time do you need?
It's okay, you can erase. Okay, you can erase now.
Good. Now it's you guys to tell me what to do. I want to expand x plus 2y or 5 using binomial theorem. Using binomial theorem. What must I do? Tell me what to do. I want to do this expansion using binomial theorem. The first term is x. The second term is 2y. How do you do this? Anyone else to try? Hello? Kate. Kate, are you there?
Can you hear you?
Yes, how do we do this? We want to expand this term using binomial theorem. So the theorem tells you this guy should be summation from j is 0 to 5 of 5 combination j of x raised to 5 minus j and then 2y raised to j. So when j is 0, I have 5 combination 0. And then here I will have x power 5. Plus, when j is 1, I have 5 combination 1. And then x to the 4, 2y to the 1. When j is 2, I have 5 combination 2, x cubed, 2y squared, plus when j is 3, 5 combination 3, x squared, 2y cubed, plus at j is 4, I have 5 combination 4, x to the 1, 2y to the 4, plus 5 combination 5. So now j is 5, x to the 0, 2y to the 5. This is what the theorem tells us. So this first guy, 5 combination 0, any number combination 0 is 1. 5 combination 0 is 1. So we'll have x power.
I'm taking one of the shots. Put down. Hey. Here's one. All right, keep moving. It's great.
Let's continue. Sorry about that. I had to remove it. There's nothing I can do. So 5 combination 0 is going to be 1. This is very easy to compute. 5 combination 0 is 5 factorial divided by 0 factorial times 5 minus 0 factorial. So you have up here 5 factorial. 0 factorial we know is 1. 5 minus 0 is 5. So 5 factorial divided by 5 factorial is 1. Then I have x to the 5. So this term, we're done with that. We move to the second term. 5 combination 1. So when I have 5 combination 1, this becomes 1, this becomes 1. So this should be 5 factorial divided by 1 and then times. So 1 times 4 factorial. There's actually a shortcut. You can do this with your calculators. If you have your calculators, there's this key written NCR. If you've seen this key NCR, it should compute for you n combination R. This computes n combination R from your calculator. For those who have calculators, I will show you how to do this short. But this should give you 5 because you can write 5 factorial as 5 times 4 factorial divided by 4 factorial. So these guys, you have a 1. So you have 5 x to the 4 times 2y. Now, let me, to save on time, let me just give you the coefficients because I know them. I will show you how to get them from a calculator for those who have a calculator, but it's just a matter of applying the definition. 5 combination 2 should be 10. So then you have x cubed, and then 2y squared. 5 combination 3, that's also 10. Then you have x squared, 2y cubed. 5 combination 4 is 5. So we have 5x and 2y to the 4. Lastly, 5 combination 5 is 1. Then we have 2y to the 5. Let us finish up this. What does it look like? So this is going to be x to the 5 plus 2 times 5 is 10. So this is 10 x to the 4 y plus. There's a 2 squared somewhere times 10. That gives you 40. So this is 40 x cubed y squared plus. There's a 2 cubed. 2 cubed is 8 times 10. That is 80. So 80 x squared y cubed plus 2 to the 4 is 16. 16 times 5, that's 80 x y to the 4 plus 2 to the 5 is 32. So we have 32 y to the 5. We were looking for the term that contains x cubed y squared. So let's see. X cubed y squared is right here. And this is exactly what we obtained here. So with binomial theorem, I can obtain the particular term that I'm interested in without doing the whole expansion. So I obtained this from the theorem without doing the whole expansion. I just did the expansion to check if it is true that this is the particular term. Any questions? Any question?
Yes, can you hear me?
Yes, I can hear you.
Yeah, can you please repeat how you did it without using all this formula?
Without, well, I've done it so many times, so I just know that. I know some of them. It's a very easy pattern to master, but you don't need that. Let me show you a shortcut, maybe. A shortcut of computing this. Is this okay for everyone? Apart from the question that you've asked? You guys are so dull today. So what we gave us the definition, we said n factorial is n times n minus 1 all the way to 2 up to 1. notice that from n-1 going on, you could write this as n times n-1 factorial. So it's okay to write 5 factorial as 5 times 4 factorial, which is 5 times 4 times 3 factorial. Now, if I want to compute, let's say 5 combination 3. By definition, I need 5 factorial, divide by 3 factorial, and then divide by 5 minus 3, which is 2 factorial. 5 factorial is simply 5 times 4 times 3 factorial. You can stop at 3. Then down here I have 3 factorial times 2 factorial. 3 factorial cancels 3 factorial because this is just a definition. 2 factorial is 2. 2 will divide 4 2 times. So 5 times 2 gives you 10. Let me use a bigger number. A bigger number. Suppose you want to compute, let's say 10 combination 6. Then by definition, I need 10 factorial divided by 6 factorial times 10 minus 6 factorial. So this is going to be 10 times 9 times 8 times 7 times 6 factorial divided by 6 factorial times 4 factorial, where 4 is 10 minus 6. So 6 factorial will divide 6 factorial. I don't need everybody that's away. So now 4 factorial, this is now very simple. This is now 10 times 9 times 8 times 7. 4 factorial, we all know that is 4 times 3 times 2. So now 3 divides 9 3 times. 4 divides 8 2 times. 2 divides 2. So what do we have? 10 times 3, which is 30, times 7, that is 210. Those of you who have a calculator, press this key, 10 combination 6, it should give you 210. So let me share my screen and show you how to use the, let me see if I have it calculator. Have what I'm looking for. This one doesn't have. So we'll go online. We'll go online. Scientific calculator. If you're seeing my screen. Hello?
Yes.
Yes, we can see.
Online scientific calculator. Series. This doesn't have the keys that I'm looking for. Let me specify combinations and permutations. These are permutations of data. Yes, so number of things, 10. I want to choose 6. You notice that here they have said, notice that here they have said n must be greater than or equal to r must be greater than or equal to 0. If this is not true, you will get errors. So let's compute that. Execute. This is this is number of computations, not just the combination. I want the permutation. Sorry, I computed something else. type combination would. So I just 10 combination 6. From. Let's see what we get. Wolfram is taking long. Fx into 1 online calculator. Submitted Wolfram, but it's not. Okay, here we go. 210. Are you seeing this? Hello? Hello?
Yes, I can
Yes,
see.
yes.
Yeah, so what this Wolfram has done, it has taken a list of 10 items from 1 to 3 up to 10. It has given me all the 210 possible ways of choosing 6 items. So it's 210 as we got. But I wanted a calculator that has that key. I don't know why. This guy.